Welcome to today's session. In this problem, we will explore an interesting challenge titled Maximum Value of K Coins from Piles. This problem involves selecting coins from multiple piles to maximize their total value. We'll review the problem, analyze different approaches, and break it down step by step. Let's dive in. Imagine you have several piles of coins, and each pile is represented as an array of numbers. These numbers indicate the value of the coins in that pile. The key rule here is that you can only take coins from the top of a pile downward, no skipping around within a pile is allowed. Now, you're also given a limit, an integer k that specifies the maximum number of coins you can pick in total across all the piles. Your goal is to determine the maximum value you can collect by carefully selecting up to k coins. The input consists of the pile's array, representing the coin values in each pile, and the integer k. The output will be a single integer, representing the maximum value of coins you can collect under these constraints. For example, consider the input where the piles are 1, 103, 7, 8, 9, and k is 2. To achieve the maximum value, you could pick the top coin from the first pile, which has a value of 1, and then pick the top coin from the second pile, which has a value of 100. Adding these together gives a total of 101. As a result, the output for this case is 101. In another example, if the input is 100, 200, 300, and k is 2, you can pick the top coin from the first pile with a value of 100, and the top coin from the second pile with a value of 200. This gives a total value of 100 plus 200, which equals 500. Now, let's look at a more complex example. Suppose the input is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and k is 5. Here, you can maximize your total value by taking all 5 coins from the first pile. The sum of these coins is 1 plus 2 plus 3 plus 4 plus 5, which equals 15. Then, with the remaining capacity to pick coins, you can take the next 4 coins from the second pile, which add up to 6 plus 7 plus 8 plus 9, giving 25. Adding these together results in a total value of 15 plus 25, which equals 40. This demonstrates how you can strategically select coins to maximize their combined value while staying within the limit of k. The problem comes with several important constraints. First, the number of piles, n, is at most 100, and each pile can contain up to 2,000 coins. The value of each coin is a positive integer up to 100,000. Additionally, the limit k can be as large as the total number of coins across all piles, meaning you may need to consider up to 200,000 coins. Some edge cases are worth noting. If there's only one pile with fewer coins than k, you can simply take all the coins in that pile. If k matches the total number of coins, you can take every coin from every pile. Lastly, when all piles have only one coin, you should prioritize selecting the largest values. Given these constraints, an efficient algorithm is needed to solve the problem, and a dynamic programming approach is a good fit for balancing the trade-offs between selecting coins from different piles while maximizing their total value. To solve this problem, we first consider a brute force approach. The intuition here is straightforward. We generate all possible combinations of coins that can be chosen from the given piles. For each pile, we decide how many coins to take, ranging from 0 to either the size of the pile or the maximum limit k. Then, for each combination, we compute the sum of the selected coins and find the maximum value. While this method is conceptually simple, it quickly becomes computationally infeasible as the input size grows. The time complexity is exponential, specifically s to the power of k, where s is the average size of a pile, making it impractical for larger inputs. The space complexity is k, which accounts for the recursion stack if implemented recursively. To address these inefficiencies, we turn to an optimized dynamic programming approach. The key idea here is to break the problem into smaller subproblems and leverage overlapping subproblems, thus avoiding redundant calculations. We define a dp state, dp, I, k, as the maximum value we can achieve by selecting k coins from the first I piles. This state allows us to systematically compute the solution by considering all possible choices of coins from the current pile and combining them with already solved subproblems for the remaining piles. To compute dp, I, k, we evaluate all possible numbers of coins we can take from the current pile, ranging from 0 to the minimum of k in the pile size. For each choice, we calculate the value of the selected coins and add it to the result of solving the subproblem for the remaining coins in piles. The recurrence relation for this is expressed as dp I, k, equals the maximum of dp I1, kj, plus the sum of the first j coins from the current pile, for all valid j. The base case is straightforward, dp 0, k equals 0, since no coins can be taken if there are no piles. Analyzing the complexity, the time complexity is O, n asterisk k asterisk s, where n is the number of piles, k is the maximum number of coins, and s represents the average size of a pile. This accounts for the computation of prefix sums and the dp table. Space complexity is O, n asterisk k, which is required to store the dp table. While a greedy approach might seem tempting, where we always pick the largest available coins, this strategy fails in scenarios where taking fewer coins from one pile leads to better options in subsequent piles. Therefore, a greedy approach is not viable for this problem. Based on these considerations, we select the optimized dynamic programming strategy as our solution. It strikes an excellent balance between efficiency and correctness, effectively addressing the input constraints while ensuring that we find the optimal result. The decision to use dynamic programming is supported by key observations. First, we utilize prefix sums to efficiently compute the sum of the first j coins in a pile. This pre-processing step, which has a linear cost of O, s, per pile, significantly simplifies the calculations within the dp loop. Second, the problem exhibits overlapping subproblems, since the decision to take j coins from the current pile reduces to solving the subproblem for the remaining piles and kj coins. Third, it demonstrates optimal substructure, meaning the overall solution can be derived by combining solutions to smaller subproblems. When comparing the trade-offs, the dp approach is far superior to brute force due to its polynomial time complexity. While it does require additional space to store the dp table, this is a reasonable trade-off given the substantial performance improvement. Additionally, the pre-processing cost for prefix sums is minimal and pays off by streamlining the dynamic programming computations. In conclusion, dynamic programming is the best choice for solving this problem within the given constraints. It ensures efficiency, correctness, and scalability, making it the optimal strategy to maximize the value of coins we can collect from the piles. To solve this problem, we need to determine the maximum sum of values that can be obtained by selecting coins from multiple piles, with the restriction that we can choose at most k coins in total. Each pile contains a specific number of coins, each with its own value, and we aim to identify the optimal selection strategy to maximize the sum while adhering to the constraints. One straightforward way to approach this is through a brute force method. The first step involves generating all possible combinations of coin selections. For each pile, we consider every possible number of coins to take, ranging from 0 up to the size of the pile, ensuring the total number of coins selected across all piles doesn't exceed k. We then use a recursive function to systematically explore these combinations. Once we have the combinations, the next step is to compute the sum of the selected coin values for each one. If a combination violates the constraint of selecting more than k coins, we discard it. Finally, we track the highest sum encountered during this process and use that as our result. While this approach is conceptually simple, it is computationally expensive due to the sheer number of combinations that need to be explored. After exploring all possible combinations, the brute force approach concludes by returning the highest sum found as the result. This method ensures that every potential solution is considered, making it guaranteed to find the optimal answer. However, it comes with significant computational challenges. Because the number of combinations grows exponentially with the number of piles, this approach becomes impractical for larger inputs. This is what's known as combinatorial explosion, where the number of possibilities increases drastically with the problem size. To implement this approach, we rely on a recursive function called stack, which allows us to systematically explore all possible combinations of coin selections. The stack keeps track of which pile we're currently processing, how many coins we've selected so far, and the running sum of their values. Additionally, temporary storage is used to keep track of the current combination of coins chosen from each pile during the recursive exploration. These data structures help manage the complexity of the brute force method, but they also highlight its inefficiency when dealing with larger datasets. To better understand the brute force algorithm, let's walk through an example. Suppose we have 3 piles. The first pile contains coins with values 1, 2, 3, the second pile has 4, 5, and the third pile contains 6. We are allowed to select up to k equals 3 coins in total. The process begins with recursive exploration. Starting with the first pile, we consider how many coins to take, ranging from 0 to the size of the pile. For instance, we could take 0, 1, 2, or all 3 coins from this pile. If we choose one coin, say the coin with value 1, we then move to the second pile and repeat the process, deciding how many coins to take from it. At each step, we add the selected coins' values to a running sum. If the total number of coins selected exceeds k at any point, we discard that combination and stop further exploration of that branch. After evaluating all combinations for a given selection, we compare the running sum with the current maximum sum. If the new sum is greater, we update the maximum. This process is repeated until every possible valid combination has been explored. Once all combinations have been evaluated, the algorithm returns the maximum sum as the result. While this method guarantees correctness, its inefficiency becomes evident when we analyze its time complexity. The total number of combinations is proportional to the product of the sizes of the piles. In the worst-case scenario, this results in a time complexity of O, m to the power of n, where m is the average size of the piles and n is the number of piles. Additionally, for each combination, calculating the sum of selected coin values takes O, n, time. Combining these factors, the overall time complexity becomes O, m to the power of n asterisk n, making it infeasible for larger inputs. The space complexity is primarily determined by the depth of the recursive call stack, which is at most n, corresponding to the number of piles. Temporary storage used to hold the current combination of selected coins also contributes to the space usage, but it is relatively small in comparison. Overall, the space complexity is O, n. This analysis underscores why the brute force approach is impractical for larger problem instances, despite its simplicity and guaranteed correctness. To address the inefficiencies of the brute force method, we can apply several key optimizations. First, pruning allows us to stop exploring a branch as soon as the total number of selected coins exceeds k, eliminating unnecessary computations. Second, memoization can be used to store the results of previously computed subproblems, avoiding redundant calculations when encountering similar states during recursion. Finally, the brute force approach can be replaced altogether with a dynamic programming solution, which significantly reduces computational complexity by solving the problem iteratively and reusing intermediate results. When implementing these optimizations, it's crucial to consider edge cases. For example, if one or more piles are empty, the algorithm must handle this gracefully. Similarly, if k equals 0, the result should be 0 since no coins can be selected. For large values of n or k, the brute force method becomes infeasible, making these optimizations essential for achieving reasonable runtimes. These enhancements transform the problem from being computationally prohibitive to solvable within practical constraints, even for larger inputs. Here, we define a class called solution and implement the function maxValueOfCoins. This function takes two inputs, a list of piles, where each pile contains coins, and an integer k, which represents the maximum number of coins we can pick. We begin by calculating the total number of piles, n, and then pre-compute prefix sums for each pile. The prefix sums allow us to quickly calculate the total value of taking a specific number of coins from a pile. For each pile, we initialize a prefix list with 0, and as we iterate through the coins in the pile, we append the cumulative sum of coins to this list. These prefix sums are stored in a list called prefix_sums. Next, we initialize a memoization dictionary, memo, which will be used to store the results of subproblems and avoid redundant calculations. The main logic is implemented in a helper function, dp, that takes two parameters, the index of the current pile, I, and the number of remaining coins we are allowed to pick, remaining. Inside dp, the base case handles scenarios where either all piles have been processed or no coins can be taken. In such cases, the function simply returns 0. Additionally, if the result for a given state has already been computed and cached in memo, we return it directly to save computation time. One of the choices we evaluate is to skip the current pile entirely, where we recursively call dp for the next pile while keeping the remaining count unchanged. Another choice in the DP function is to take coins from the current pile. Here, we iterate through the possible numbers of coins we can take from the current pile, ranging from 1 to the minimum of the pile size or the remaining coins. For each number of coins taken, we calculate the total value by adding the corresponding prefix sum from the current pile to the result of a recursive call to DP with the next pile and the updated remaining count. We continuously update max_value to store the maximum value achievable for this state. Once all options are evaluated, we store the result in the memo dictionary to cache it for future use. Finally, the function returns the maximum value for the current state. At the end of the implementation, we initiate the recursion by calling DP with the first pile and the total number of coins available, k. This starts the process of exploring all possible ways to select coins from the piles to maximize their total value, leveraging memoization for efficiency. Here, we start by importing the necessary Java utilities and defining the solution class, which contains our main method maxValueOfCoins. The goal of this method is to calculate the maximum value we can collect by choosing up to k coins from a list of piles. First, we determine the total number of piles, n, and then proceed to pre-compute the prefix sums for each pile. The prefix sums allow us to quickly calculate the total value of taking any number of coins from the beginning of a pile, which is crucial for optimizing our solution. Each pile's prefix sum starts with a 0 to represent taking no coins, and we iteratively add the value of each coin to build the prefix list. Once these prefix sums are calculated for all piles, we initialize a hash map called memo to store intermediate results and avoid redundant calculations during recursion. Finally, we call the recursive helper method DP, passing the starting index, the remaining coin quota, and our pre-computed data structures as arguments. The DP function is where the main logic of our solution resides. It starts by handling the base cases. If we have processed all piles or if there are no remaining coins to pick, we simply return 0 because no value can be added. Next, we construct a unique key from the current index and remaining coins to check if the result for this state is already cached in the memo map. If it is, we return the cached result, avoiding unnecessary recalculations. Now, we evaluate two options: either skip the current pile entirely, or take coins from it. To skip, we recursively call DP for the next pile, keeping the remaining quota unchanged. To take coins, we iterate over all possible numbers of coins we can take from the current pile, up to the lesser of the pile size or the remaining quota. For each choice, we calculate the total value by adding the prefix sum for that number of coins to the result of a recursive call for the next pile with the updated quota. The maximum value across all choices is stored in maxValue, which we then cache in memo before returning it. This ensures our solution is both optimal and efficient. In this example, we are given 3 piles of coins and need to select up to 4 coins in total to maximize their value. The first step is to pre-compute the prefix sums for each pile. These prefix sums allow us to quickly calculate the sum of coins if we choose to take a certain number from any pile. For instance, in the first pile, taking 1 coin gives a sum of 1, taking 2 coins gives a sum of 3, and so on. Once the prefix sums are ready, we initialize the recursion starting with pile 0 and 4 coins available. At this point, we have two main options: either skip the pile entirely and move to the next pile, keeping all 4 coins available, or take some coins from the current pile. If we decide to take coins, we can explore taking 1, 2, or all 3 coins from pile 0. For example, taking 2 coins would add 3 to our total and leave us with 2 coins to distribute across the remaining piles. Each of these decisions leads to a new recursive call, where we continue the process for the next pile with the updated number of coins available. At pile 1, we continue the decision-making process with the remaining coins. Here, we again have the option to skip the pile entirely or take a certain number of coins. If we decide to take coins, we can explore taking 1, 2, or all 3 coins, depending on how many are still available. For each choice, we add the corresponding prefix sum from pile 1 and make a recursive call for pile 2. When we reach pile 2, the process is similar. We decide whether to skip the pile or take a certain number of coins, using the prefix sums to calculate the value added. Throughout this process, we use memoization to store the results of overlapping subproblems. This ensures that we don't recompute values for the same state, significantly improving efficiency. After exploring all possible combinations of choices across the piles, we determine that the maximum value we can achieve with 4 coins is 18. In this second example, we consider an edge case with smaller piles and only 2 coins available. The prefix sums for these piles are pre-computed as usual, allowing us to quickly evaluate the value of taking any number of coins from each pile. Starting with pile 0 and 2 coins, we have the option to skip it or take 1 coin. If we take 1 coin, we add 5 to our total and proceed with 1 coin remaining. At pile 1, we once again decide whether to skip it or take a coin. Taking 1 coin from pile 1 adds 10 to our total. Finally, at pile 2, with 1 coin remaining, we take 1 coin, adding 30. By considering all possible combinations, we determine that the maximum value achievable in this case is 35. In the final example, we examine a scenario where the total number of coins to be selected equals the total number of coins available across all piles. After pre-computing the prefix sums, we begin with pile 0 and 6 coins. Since we can take all coins, the process becomes straightforward. We take all the coins from each pile. For pile 0, this adds 3 to our total, for pile 1, it adds 7, and for pile 2, it adds 11. Summing these values gives us a final maximum value of 21. This example highlights the simplicity of the solution when k matches the total number of coins, as there's no need to make any decisions, every coin is selected. To analyze the time complexity of our solution, we start with the pre-processing step. For each pile, we calculate its prefix sums, which helps us quickly compute the sum of coins when making choices later. If there are n piles and the maximum number of coins in any pile is m, computing prefix sums for one pile takes m time. Doing this for all piles results in a total time complexity of n*m for this step. Next, we consider the recursive function combined with memoization. The function dp(i) remaining evaluates 2 main choices for each pile, either skipping the pile entirely or taking a certain number of coins from it. The number of coins taken can range from 0 to the smaller of the pile size or the remaining coin limit, which means the inner loop has at most m iterations. The recursive state space is defined by the 2 parameters, the pile index I and the remaining coins remaining. Since there are n piles and up to k remaining coins, there are n*k unique states. For each state, the inner loop iterates up to m times, leading to a total computational cost of n*k*m for the recursive function. When combining the 2 components, the overall time complexity is determined by adding the costs of prefix sum computation and the recursive function. Computing prefix sums contributes n*m, while the recursive function with memoization contributes n*k*m. Therefore, the total time complexity is dominated by the larger term, which is n*k*m. Now turning to space complexity, we first consider the storage required for prefix sums. For each pile, storing the prefix sums takes m space, and with n piles, this totals to n*m. Next, we factor in the memoization table, which stores results for all unique states, I, remaining. With n*k states in each requiring 1 space, the memoization table contributes n*k to the space complexity. Lastly, the recursive stack depth is proportional to the number of piles, which is at most n. Since each stack frame requires constant space, the stack contributes n additional space. These components together make up the total space complexity. To summarize the overall space complexity, the largest contributors are the prefix sums and the memoization table. The prefix sums require n*m space, while the memoization table contributes n*k. Adding these together gives a total space complexity of n*m plus n*k. Comparing this dynamic programming solution to a brute force approach highlights its efficiency. A brute force method would involve generating all possible ways to select up to k coins across n piles, which is exponential in nature. Specifically, the number of combinations would lead to a time complexity of m to the power of k, where m is the maximum pile size. This quickly becomes infeasible for large inputs. By contrast, the dynamic programming approach avoids redundant calculations through memoization and uses prefix sums to efficiently compute coin sums. This optimization reduces the time complexity to n*k*m, making it a far superior approach for solving this problem. analyzing the best and worst cases, the time complexity remains O and *k*m in both scenarios. Even when parameters like k or m are small, the algorithm still needs to process all relevant states and piles, maintaining the same asymptotic complexity. In the worst case, where n, k, and m are all large, the algorithm will explore every state and iteration, fully utilizing the O and *k*m operations. Mathematically, the efficiency of this approach stems from the fact that each state, I, remaining, is computed only once. The inner loop for each state runs in O, m, and with O and *k states overall, the total number of operations remains bounded by O and *k*m. The space complexity, dominated by the prefix sums in memoization table, totals to O and *m plus n *k. This dynamic programming solution effectively balances time and space trade-offs, transforming what would have been an exponential brute force method into a polynomial time solution. By leveraging pre-processing and memoization, it ensures efficiency while adhering to the constraints of the problem. Let's go over some common mistakes to avoid when solving this problem. First, it's crucial not to overlook base cases. Many recursive or dynamic programming problems rely heavily on properly defined base cases to prevent errors. For example, if the input piles are empty or k is 0, the function should return 0 immediately. Failing to handle such cases might lead to infinite recursion or incorrect outputs. Another frequent issue is not pruning suboptimal states. In a brute force approach, exploring every combination without eliminating invalid or unnecessary options can lead to exponential time complexity. For instance, if you've already selected k coins, there's no reason to continue exploring that branch further. Finally, when using dynamic programming, it's essential to manage the state correctly. The state should fully represent the problem at hand. For example, if the state is defined as dp, I, k, it needs to reflect the maximum value you can achieve by selecting k coins from the first I piles. A poorly defined state can result in missed overlapping subproblems and produce incorrect results. Now, another common pitfall is making off-by-one errors in loops. This can happen when iterating through piles or coin counts. For instance, iterating from 0 to n instead of 0 to n1 can easily cause issues. Always double-check your loop bounds to ensure correctness. Additionally, it's important to consider constraints on k. If k is larger than the total number of coins available across all piles, your solution must account for this edge case. Ignoring such scenarios can lead to index out-of-bounds errors or invalid results. Shifting focus to interview-specific insights, it's helpful to understand the broader patterns of problems like this. Challenges involving piles or groups often map to well-known problem types such as the knapsack problem or combinatorial optimization. Clarifying constraints, such as whether repetition is allowed or if choices are mutually exclusive, is key to formulating a correct approach. Lastly, dynamic programming solutions can often be optimized further by reducing state dimensions. For example, instead of maintaining dp, I, k for all I, you can use rolling arrays to reduce the space complexity to O, k, which can be a valuable optimization in interviews. It's also important to clearly communicate trade-offs in your approach. For instance, while a brute force method might be easier to implement, it's computationally expensive and impractical for larger inputs. On the other hand, optimized approaches like dynamic programming offer better performance but come with added complexity. Being able to articulate these trade-offs demonstrates a deeper understanding of the problem. If your solution involves recursion, it's vital to explain the recursive relation, how base cases are set up, and how memoization is used to avoid redundant computations. This clarity not only shows your problem-solving skills but also your ability to break down complex solutions. Additionally, it's helpful to familiarize yourself with related problems that have similar structures or techniques. For example, LeetCode problems like 1049, 416, 494, and 518 all involve variations of combinatorial optimization and can provide valuable practice for honing your skills. Finally, let's discuss some alternative approaches and the trade-offs involved. A brute force approach is the simplest to implement but has exponential time complexity, making it suitable only for small inputs where constraints allow. Dynamic programming, on the other hand, can be implemented in two ways. The top-down approach, which uses recursion with memoization, is intuitive and works well for larger problems, but it may require additional memory. Bottom-up dynamic programming, while more space-efficient, especially with rolling arrays, can be less intuitive and harder to debug. Transitioning from top-down to bottom-up often introduces its own challenges. Lastly, a greedy approach, if applicable, can be a quick and simple solution. However, it only works for problems that exhibit the greedy choice property, meaning local optimal choices lead to a global optimum. This makes it less universally applicable, but worth considering for simplified versions of the problem. Understanding these trade-offs will help you select the best approach based on the problem's constraints and requirements. Great job! To recap, we tackled the problem maximum value of k-coins from piles, reviewed approaches like brute force and dynamic programming, and discussed their efficiencies. Remember to practice similar problems to solidify your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!